Interactive math reviews for 1314 and Math 1324, presented by Vechuca, Ruben Carrizales, and Albert Isasi. This session will be recorded so that you may come back to it at a later time, and also for those who may have missed today's presentation, may be able to watch it at a more convenient time. Thank you. So now at this time, please mute your mics for the best sound experience. We don't want any of the feedback interfering with today's important lesson. This presentation will provide Tejano passport points. Okay, so the code will be posted on the chat at the end of the session for the Tejano passport points. Without further ado, here's Mr. Ruben Carrizales.
Good morning, everyone, and thank you again for joining us this Friday for our Happy Math Hour. I hope you all had a great week after having a week off of spring break. So back to the math, right? So let's go ahead and give a couple of seconds for those of you who are here to do Math 1324. You'll find the link on your chat. Just go ahead and click on that, and you'll be directed into that session. If you're here for the Math 1314, you'll just stay here. All right, so for those of you Math 1314, today's session is going to be over exponential and logarithmic functions. So let's get started. So first, let's define what an exponential function is. And your book's definition, the formal definition, says that an exponential function f has a base a, and it's denoted by this syntax, right? F of x is equal to a to the x, where a has to be greater than 0 and a cannot be 1. X is any real number, okay? So when we are looking at an exponential functions, the characteristics that we always have to keep in mind is the domain of f is a set of all real numbers. And I need to let you know, we're going to do transformations of a lot of the exponential functions, but the domain will remain constant. This will never change. It will always be the set of all real numbers. On the other hand, the range, which is all the y values, this one is going to change. And again, this is all, and as far as if I was thinking of just the parent function or the function that they're giving me here, currently in its state, its range is a set of all positive real numbers. So just the positive real numbers, okay? But this one, it will change according to all the other children of the graphs, okay? So I have this riddle for you, okay? And I always like to tell my students is just to see the importance of how exponential functions work and why is it extremely important learning how to round and rounding correctly. Okay, so suppose that you receive a penny on the first day of class and 2 pennies on the second day, 4 pennies on the third day, and so on and so forth. Okay, this would continue until 31 days. Now, if I were to do this, okay, give you 2 pennies and double it for 31 days, would you rather take this option of pennies, or would you rather receive a lump sum amount of, let's say, $1 million? Okay, so if you were to put this on a calculator, okay, do 2 pennies and double them for 31 days, what you would discover is if I were to do a table, okay, the first day, 1 penny, second day, 2 pennies, and so on and so forth, okay, this can be represented as exponents, to the 1, to the second, to the third, so on and so forth until I got to 2 to the 31, right? And what you would see is that to get your answer, you would put it on your calculator, 2 to the 30th power, okay? Now, what is 2 to the 30th power? So if I do this, again, this would give me 1 billion, but again, we're dealing with pennies. So and there is 100 pennies in a dollar, right? So we would need to move the decimal to the left 2 units to find the dollar amounts. But we would still end up with this amount, $10,737, right? So if someone came up to you and said, would you like to have pennies doubled for 30 days, or would you just like $1 million? go with the penny option. Okay, but again, the whole point of this riddle is to emphasize that when doing exponential problems, you cannot round, because if you round and your rounding is off by a penny, that means your answer is going to be off by dollars. Okay, so it's very, very important that you round correctly, and the best thing to do when solving exponential problems is to not round until the end. Use all the numbers that your calculator gives you in order to solve these exponential functions. Okay. Now, I also like to mention, you in the movies or somewhere, right? You've heard that situations are growing exponentially. Well, what do they mean by that? Well, just like the pennies grew, 2 pennies grew to $10 million. That means that when we're dealing with exponents, the values grow really, really fast. Okay, so these are things to consider and think about. So, again, this scenario that I just mentioned to you is basically is my parent exponential function. F of x is equal to 2 to the x. Okay. Um, Now, we're going to be using this function to go ahead and explain the graphs of our characteristics. Okay, so this is a summarization of our basic characteristics of our exponential function. All right, so if I have a function or an equation that is in this form, y is equal to a to the x. Again, a has to be greater than 1, and x has to be a value greater than 1 as well. So it's here, my domain, if you see the graph, even though you don't see arrows here, there's an arrow. This graph goes forever to the left and goes forever to the right. So my domain is negative infinity to positive infinity. Remember, our domain is all the x values that the graph has. The range refers to all the y values that the graph represents. And if you see here, um, the graph does not cross or touch this horizontal axis. This means that I have a y equals 0 here, horizontal line. The graph does not touch it, so it gives me the range is all positive real numbers, right? So here, when we're reading graphs, we're reading graphs from left to right. So you see that this graph is increasing. It's going from small to big, and it's growing and it's growing, it's growing. So this is an increasing graph. Now, this concept that I just mentioned, that this graph does not cross our horizontal line here, x equals 0, this is our asymptote. And we all should be familiar now with asymptotes because we went over asymptotes when we were looking at rational functions, correct? So our exponential function is also going to have a asymptote, but it's going to be a horizontal asymptote, okay? So which is our x-axis, and if I would write this as an equation, it would be y equals 0, okay? Now, the last point here of our characteristics is that this graph is a continuous graph. What does that mean? That means that this graph has no sharp turns. There is no breaks in the graphs. And again, what we learned from high school is when we're looking at continuous graphs, is if we can draw a graph without lifting our pencil, right, or doing sharp turns, they're smooth curves or lines. Yes. All right. So these are our basic characteristics of our exponential function. Now, let's look at this example here. What if my exponent was a negative x? It's nice to have it in this format because it's going to tell you that this graph, instead of it growing, increasing, it's going to be decreasing. But the major point that we want to point out is that we can use our basic rules of exponents, because there's no such thing as a negative exponent. We can convert this into a positive exponent by taking the negative reciprocal of this, right? So the negative reciprocal of 2 negative x is 1 over 2 to the x. This is the positive value. So I like to give this example because 2 to the negative x is the exact same thing as 1 over 2 to the x. But again, I like this format better, the 2 to the negative x, because this tells me that, hey, I have a decreasing graph. Okay, so if I look at the characteristics of this example here, okay, I see that my domain is still the same. And remember, please keep in mind, I can look at any transformation of the exponential function, and this domain will never change. It's always going to be in interval notation from negative infinity to positive infinity. Now, my range in this particular one, it didn't change because it was just a reflection on the y-axis. So the range is still from 0 to positive infinity. My horizontal asymptote still did not change. It's still the x-axis, or in equation format, y equals 0. Okay, and again, this is decreasing. We read this graph from left to right again, and we see that we go from a high value to smaller and smaller and smaller. It's decreasing. Okay, and again, this graph is still continuous. Okay, all right. So what if we wanted to graph a function that is something other than that base 2 as our parent that I had mentioned to you? Well, let's think about the riddle problem, right? So if I gave you 2 pennies and double it, you saw that our amount grew. But what if I said I gave you 3 pennies? Well, hopefully you would see that instead of 2 pennies, I give you 3 pennies, and that means that my graph is going to grow even much faster. That the amount after let's say 30 days, it's going to be tremendous, right? It's going to be exponential, right? It's going to be a large number. So we can go ahead and construct tables and go over to see how this graph behaves. Okay? So to first to get an idea of plotting points and to see how this graph behaves, we can randomly pick values for x. And here in my case, I just picked x equals -2, -1, 0, and 1. And when I plug it into my function, again, in order to evaluate 3 to the -2, I'm going to take the negative reciprocal, and it's going to give me 1 over 3 squared, which gives me 1 over 9. Same thing with the -1, the 0. Now, let me also focus on this one. Please keep in mind, and just a reminder, that anything to the 0 power, the answer will always be 1. So for instance, here, 3 to the 0, the answer is 1. But if I had 1 million to the 0 power, the answer is 1. If I had x to the 0 power, the answer is always 1. Anything to the exponent of the 0 the answer is always 1. Okay? And then we have our identity here, 3 to the 1 is just 3. And so if I were to plot these points, okay, you see that my graph has like this. It's going to be very similar to the graphs that we had been seeing, except that it's hard to tell, but the curve is going to be a lot steeper than the one that we wrote, that we saw before. And this is just a nicer version that grabbed from the calculator. But again, this function, even though you don't see it, and because this was a computer-generated graph, this green line, again, is getting very, very close to my horizontal axis. But again, it's never going to touch it. It's never going to cross. I know it kind of looks like it's becoming the x-axis, but just please keep in mind that it's not. It's not crossing or even touching it. It's just getting very, very, very close, and very, very small values close to that 0, but never will become 0. Okay. All right. So here, what we can do is we can determine if we have a function. If you remember, to determine if we have a function, we can provide the vertical line test. And for us to do this, is we want to always see that if a function has an inverse or an opposite, okay, we would perform the horizontal line test. And if these both tests pass, if my graph, by applying the vertical line test and horizontal line test, passes, that means that my function, one, has an inverse, and we say that it's 1 to 1. Okay, so if I'm finding to see if this is a function, if my exponential function is a function, again, we would perform our vertical line test, and we would see that it passes. Okay, and if we would perform our horizontal lines to see if it has an opposite or an inverse, we would see that this function will also pass. So we would say that this function is 1 to 1. Now, um, the reason why I'm saying this is because what we can do is apply this 1 to 1 property when wanting to solve for exponential functions. And let me elaborate more what we have here. And this is a textbook definition of a 1 to 1 property. So if I have an equation, and this equation, we have an exponent on the left and an exponent on the right. The only way that the left side is equal to the right side is if we are dealing both with the same base, and in this case, we see that it has the same base. But this is also telling me that the exponents, xy, would have to be equal to each other. That's the only way that this equation is a true statement. That first we have to have the same base on both sides, and the exponents have to be equal on both sides for this to be equal, okay, or a true statement. So let's look at an example of using our one-to-one property to determine or solve two exponential functions or an exponential function equation. So if we see here, we have 10 to the 2 minus 4x is equal to 10 to the exponent 6x minus 1. Now, our question is, can we use our one-to-one property? So just by looking at our example here, we see that the left equation has a 10, the right equation has a base 10, so the bases match. So that's so far so good. But in order for us to this be a true statement, our exponential functions have to be equal. So the answer is yes. We can use our one-to-one property to solve for this. And the way we're going to do it is we're going to set our exponents equal to each other, because that's what the definition said, that for us to use the one-to-one properties, the exponent of the left has to be equal to the exponent on the right. So that's what I did here. I set the exponent of the left, which is 2 minus 4x, and on the right here is the exponent of the right side, which is just 6x minus 1. So now all I have to do is count on my friend algebra to solve for x. Okay, so let's see here. So I like to have the variable on the left and anything that just has a number on the right. So on this left side, I want to then move this 2 to the other side by subtracting 2 on both sides. And I want to move this 6x to the left side, and I'm going to do that by subtracting minus 6x on both sides. So when I do this, 2 minus 2 is 0, minus 4x minus 6x is minus 10x. On the right side here, we have 6x minus 6x is 0, and minus 1 minus 2 is minus 3. So to solve for x, I'm going to do the opposite of this multiplication of 10 by dividing by a negative 10x on both sides. And when I do that, a negative divided by a negative is going to be a positive, and the answer is just going to be 3 over 10. So I use a simple definition of our one-to-one property to be able to solve an exponential equation. Okay. All right. So let's look at another example. Let's solve this equation. Now, can you use our one-to-one property? Well, at first glance, you're saying to yourself, well, I have an exponent on the left. It has a base 4 and has an exponent of x plus 1, but the right side it's just a number. So I'm not sure. Well, the answer is we could. And the way we can do this is by rewriting 64 to be able to have a base. And we don't want just any base. What we would want, in order for us to use our one-to-one property, it has to have the same base as the left side. So what I want to convert or do is convert 64 into an exponent with a base 4. So let's see. What I would do is I can do that. Now, you're saying to yourself, well, Mr. Carrizales, how did you do that quickly, 64 to 4 to the third? Well, here, let me grab my marker here, and let me show you how I do these, okay? This one is somewhat simple. Some of us may see that exponential base, but if you don't, the way I would do it is this. Since I have a number here and I wanted to have a base 4, what I'm going to do is I'm going to do a factor tree, but not just a factor tree. I'm going to do a tree of a base 4 or a division of 4. So what I'm going to do is this. I'm going to divide 64 by 4. So if I see 4 will go into 6 one time, and 4 will with a remainder 2, and 4 will go into 24. 16, right? 6 times. So now 4 times 16 is 64. Then I would do it again. 4 can be divided into 16. That's 4 times 4 gives me 16. So see here, the trees of my leaves of 64 are 1, 2, 3, 4s. So that's how I got 4 to the third power. So now that I have converted the 64 into a base of 4 with an exponent, now I can use my one-to-one property. Since these two have the same base, my one-to-one property says that for these two exponential equations to be equal to each other, the exponents have to be the same. So that's what I'm going to do. I'm going to set my exponents equal to each other. So the exponent of the left is just x plus 1. The exponent of the right is just 3. So here's my equation. Now all I have to do is solve for x. This one's easy. I'm just going to subtract 1 on both sides. And when I do that, I'm going to get 2. Okay, and I skipped a step. I didn't put the minus 1 on both sides. So 3 minus 1 gives me the positive 2. Okay, so we can, and that's our go-to way to solve exponential equations. If we can use our one-to-one property, we want to use it all the time. Okay, so let's go ahead and look at another example. This one looks a little bit difficult, but here, let's solve this equation. The original equation is 5x minus 3 is equal to 1 over 125. Okay, so I skipped some steps from here to here, but let me go ahead and add those steps. Okay, the first thing that I'm going to do is I'm going to get that 125. Okay, that 125, I want to convert it into a base and an exponent. And again, not just any base. I see that the left side has a base 5. So what I want to do is can I make 125 have a base of 5? And again, I'm going to do a tree to do this again. So I'm going to divide by 5. So 5 will go into 12 2 times, remainder 2. 5 will go into 25 5 times. Okay, so 5 times 25 is the 125. Then I'm going to do it again. Oh, 25 is divisible by 5 again. So 25 divided by 5 is 5. Okay, so 125 can be written as 5 times 5 times 5, or as a representation as 5 cubed. Okay, so it would be half this, 5 cubed over 1. Okay, but again, this is not a base, so I can make it into a base by doing my negative reciprocal of this fraction, and the 5 would become my numerator, the 1 will become the denominator, and since the 3 went to the top, it became a negative value. Okay, so and then 5 to the negative 3 divided by 1 is just 5 to the negative 3, and voila, now I have an equation that has the same base on the left and right, and I can use my one-to-one property. And my one-to-one property says for these two equations to be equal to each other, the exponents have to be equal to each other. So I'm going to set the exponents equal to each other by having x minus 3, which is the exponent of the left, equal to just the negative 3, which is just the exponent on the right. And now, again, we rely on our friend algebra to solve for x. I'm going to add 3 on both sides. And when I do that, plus 3 minus 3 is 0, plus 3 minus 3 is 0, so x is equal to 0. Now, one thing you can do is always double check your work, okay? If I were to put 0 back here in this problem, since this one was a little bit more challenging, I always want to double check. And if I see here, if I plug in 0 for x, 0 minus 3 is just going to give me a negative 3. And 5 to the negative 3, I can convert it into 1 over 5 to the third power, and 5 to the third power we saw that it's 125. Now, can you all hear me?
Yes, Mr. Carrizales.
Oh, okay. Thank you. All right, Miss Yuka. We need to, maybe it's your computer. All right. Let's move forward. Um, so one thing that the problems that we just did before, our exponent problems, those I like to call our science or exponential functions or our science generated problems. But we also have another exponential function that works very similar to those science ones, and it's this base E exponential function. And what I tell my students is this is the business exponent for math, right? So E is just a symbol. When we say base E, it's just a symbol. And when I say symbol, think of it like the symbol pi. Most of us, we know what pi is. Pi is a symbol that represents an irrational number. And what's an irrational number? An irrational number is a number that never ends. It's a decimal value that never ends and never repeats. Okay. Now, I don't know. I just want to throw this in. Some of us math gurus, we celebrated Pi Day recently, which was March 14th. We all celebrate Pi and we all go out and have pie. But anyway, that's not what we're talking about here. So um, so going back to my example here, E is a symbol and it's an irrational number. And this is just, again, a small representation of what E is equal to, 2.7182. And again, this one goes forever. These numbers will never repeat, never end, okay? So this E is called our natural base, okay? Or our natural exponential. Like I said, we like to use this one a lot in business, okay? All right. So if I were to show you the graph of my natural exponential function, you're going to see that it has all the same behaviors that we saw before. It's going to cross the y-axis here at 0, 1, just like my parent function 2 to the x. Okay, it's an increasing function. It's continuous. It has a horizontal asymptote at y equals 0 or the x-axis. Okay, and it's continuous. All right, so let's look and solve some of our natural exponential functions, and you see that nothing changes. It's all basically the same. And for this particular one, if you notice that we can use our one-to-one property. Why? Because we have an exponential function that have the same base on both the left and the right. The base of my left side is E. The base of my right side is E. So my one-to-one property says that for these two exponential functions to be equal to each other, the exponents have to be equal to each other. So that's what I'm going to do. The exponent of the left side is just x squared minus 3, so I'm going to put that there. The exponent of the right is 2x, and I'm going to have this here. Okay, so they're giving us a little bit of a challenge. If we see here, we have a term that it has a square. So what that means, and we should all be familiar with this, we're going to have a quadratic term, right? So in order for me to solve for x, what I'm going to do is I'm going to move all the variables to one side and set this equal to 0. So when I do this, and here I got ahead of myself and told you in words, but here, this is what I'm seeing here, that this here, we have a square, so we have a quadratic. So what I'm going to do is I'm going to move all my terms to the left. So it's easier to just move one term to the left. So I'm going to move the minus 2x to the other side. So to move the 2x to the other side, I'm going to subtract 2x on both sides, which give me this. X squared minus 2x minus 3 is equal to 0. And again, we have a lot of stuff under our belts to be able to solve for x. Again, we can factor, we can use our quadratic formula. So let's see, what did I do today? My method of choice, factoring. Factoring, I love to factor. I think it's the easiest way, if it can factor, to solve for things. So I see that x squared minus 2x minus 3 can be factored into x minus 3, x plus 1. And what I did is I found two numbers that when I multiply them together give me negative 3, and when I add them together give me that negative 2. What are those two numbers? Well, it's negative 3 with a positive 1. Negative 3 times positive 1 is that negative 3, and negative 3 plus 1 is that negative 2. Okay, so to solve for this, I know that the only way that I can get 0 is if either x minus 3 is equal to 0 or x plus 1 is equal to 0. And now we can see that the solutions for this could be x equals 3 and or x equals negative 1. Okay. All right. So let's move on to the word problems, and let's look at this very famous and the most popular exponential formula. And it's the one that we have here. It's called the compound interest formula. Okay, so just for those of you who might ask, why did they label this A? Well, they label this A. They got this A from what this formula represents. It's an annuity. And the reason why I like to mention this is because this formula works in a 1 year's time. Again, annuity, if you hear that word annuity, it's like from annual or a year, right? So that's where they get that A term. But the way I want you to think of A when we're solving problems for our work, A refers to the future value, okay? And what does this mean, future value? Well, this is a formula to do business, or we're going to be dealing with money, and especially maybe even borrowed money or finance money, right? So when we borrow money, sometimes if it's your family, they might not charge you interest. But if you borrow money from a bank or from a friend or stranger, they might charge you some interest. They might say, okay, I'll lend you $10 now, but for a fee. So the future value is whatever someone loaned you plus the fee. So that's what I mean by future value. Okay. P stands for principal, but what I want you to think of the P as the present value. And there's a mistake here. This shouldn't be future. This should be present. Sorry. This is present value. Present value. It's the present. So for instance, someone loaned me $10 right now. That's what we're talking about. The P is the present value. Okay. So let's look at the other variable, the R. R refers to the interest rate, okay, or just rate. Now, keep in mind, we have a formula. In the real world, they're always going to give you the interest rate as a percent. And even when you go shopping, right? When you want to do the sales, we want to look at those sales that are 50%, 80%, right? So they give us stuff always in percent. But when we're going to use it in our formula, we need to convert this into a decimal value. Okay, this leads me to my next variable here, n. N represents what's called the compound term, or the compound periods for the year. Okay, and I'm going to go over those right now. And the last variable is t. T refers to the number of years that we're going to apply this formula. So let me talk about a little bit about our compound periods, okay, and the n values. So I am missing one here, and let me write it in. You may have in your homework a problem when they say annually. And if they say that the problem, if you're doing compound periods annually, okay, your n is going to equal 1. Okay, so that's 1 times a year. And a good example of something that happens annually is probably something that our parents are worried about, right? They have to pay taxes once a year. So taxes are something that's done annually. Okay, now the second one, the number 2, is whenever you see a word problem that they said that they're taking the interest or their compounding periods semi-annually, that means twice a year. So n is equal to 2. Okay. I always tell my students to remember the quarterly. I ask them, how many quarters are there in a dollar? 4. So if an interest or a compound period is taken quarterly, that means that our compound term or our n is equal to 4. And then we left with um, our most popular one. When you purchase the car, if anybody's purchased a car and you have to make payments, of course, our payments are once a month or monthly. So whenever you see the word monthly, our compound term or n is going to be equal to 12. Again, this is a formula that is based on a year's time. That's why it was called an annuity, right? So how many days are there in 1 year? Well, there's 365. So if you ever see a word problem that it says that the interest or the compound term is daily, then your n is going to be this value, 365. Okay. Um, Now, let's go ahead and look at some examples. Okay. Let's look at this word problem. Find the amount to which $1,500 will grow if deposited in a bank at 5.75% interest compounded quarterly for 5 years. Okay, so let's see here. When this value that they're giving me, let me get my pen again. Um, actually, I have it written down, so I don't need it. So this $1,500 is going to be my present value. This is what they're gonna. I want to deposit now. 1,500. So that's the value for P. Again, my interest that my bank is charging me, or giving me, right, is 5.75%. But I cannot use this number on the formula. Please remember to convert it into a decimal format. So remember, this percent is by dividing by 100. So to give back that division, we're going to move the decimal 2 units to the left. So this 5 will go 0.5 and then one more, 0.0575. That's the interpretation in decimal format of 5.75%. And now, we know when they said quarterly, that means that our compound term n is equal to 4. And then they said for 5 years. So the years is our time, so that's t equals 5. So let's go ahead and put everything together. And this is our formula. So I'm going to plug everything in. Now, we want to do order of operations for these, okay? So the way I would do this problem is I'm going to do first what's inside the parentheses. I'm going to do the 0.0575. I'm going to divide that by 4, okay? And then hit enter. I'm going to add 1, and then I have my answer. To that base, I'm going to take it to the exponent. Now, this I can do in my head. 4 times 5 is 20. So I'm going to take this value that I have in here to the 20th power, hit enter. And once I have my answer, I am going to multiply this value to the 1,500, where it's going to give me this, the $1,995.55. Okay. Now, also, let me see if I put it on here. I didn't, but remember, in your homework, it might not ask you to round, but since we're dealing with money, we're dealing with cents. Okay, so cents is always 2 decimal places. So if it's not specified to round, you want to always round to 2 decimal places. Okay, all right. So let's look at another finance problem here. So we have a couple that just had a baby, and they want to invest money so that they can have, so they can give it to their child for education, right? And when they turn 18, they want them to go to college or something, right? So they want to have $35,000 for them to use for college purposes, hopefully, right? So let's go ahead and solve. So it's asking us, how much should they invest? So what they're asking us, how much should our present value be now in order for us to have a future value of $35,000? Okay. So here we don't know what P is, but I'm going to use this compound interest formula here. Now my future value A is the 35,000. Again, my rate in decimal format is 0.05. This is a mistake too. This was from the previous problem. So this should be 0.0 just 58. Okay. Sorry, we copy and paste and We kept the same rate as before. All right, but on this one, our bank is going to compound daily. Oh, then that means my n is 365, and from the time the child was born till they turn 18, 18 years have passed by. So our time is going to be 18. T is equal to 18. So again, I'm going to plug everything into my calculator. And I showed you my steps on this one because this one's a little bit more complicated. Again, order of operations. So I'm first going to divide 0.058. Now this one is correct. Divided by 365, I get 0.000158904. I'm going to add 1 to that. That's going to give me 1.001588904. Again, I multiplied the 365 times 18. That gave me 6570. So this base, I'm going to take it to this exponent, which gives me this value. And now to solve for p, I'm just going to divide 2.8 on both sides. And I have this. To p is equal to 35,000 over this value here. And when I do the division, again, the couple should invest $1,322.55 now. That way, they can have $35,000 18 years from now without them having to put any more money in it. Okay. All right. So when dealing with applications, these are the two formulas that you're going to be using a lot. The first one is the compound interest formula. And then we also have a different one here. We have something that's called the continuous compound interest formula. And if you see here, the formula is given by A is equal to PERT. And again, we went over what E is. It's our little base, natural base E exponent. Okay. Now, let's go ahead and move on to section 3.2. So from 3.2, we're going to look at what the inverse or the opposite of an exponential function is, and this is a logarithmic function. So I'm going to go fairly quickly because these are very, very similar. They're just opposites to each other. Okay, so I graph here my exponential function, parent, y equals to 2x, and my parent log function here in blue. So you see here, it's a reflection on this axis or this line, this y equals to x line. Okay, now things to know. The domain of an exponential function is going to be the range of the log, and the range of an exponential function is going to be the domain of the log. Okay, they're opposites. Okay, everything is opposites for each other. I like to review. The exponential function had a y-intercept at 1. The log function is going to have an x-intercept at 1. The exponential function is going to have a horizontal asymptote. The log function is going to have a vertical asymptote. Okay, so again, we have two. We have a science log and we have a business log, or what's called our natural log. So the log of base 10 is equal to our natural log, which is just written ln x. There is no base. The base is 10. Okay. Now, let me also look at this here. When we're dealing with a log function, okay, log functions also have a base. But if we don't write the subscript here that it's a base 10, we're going to assume that it's base 10. But that's why I put these two equal to each other. If it has no base, we know that's going to be a base 10. Okay. And why is base 10? Because we have 10 digits to count, right? So that's why the natural log has no base, because we know that we're using 10 digits. Okay. All right. So one of the crucial things that is going to help us to solve and graph log functions is to be able to convert from a log to its counterpart, to its equivalent exponential form. Because some of you might know that our calculators, if it doesn't have special features like changing the base of a log, your calculators, most our basic scientific calculators only do logs of base 10. But if we have a log of base 4, we would have to do other math in order to be able to solve it. But we know that we can solve any exponential function. So that's why we want to do this conversion. I want to be able to convert this log into its exponential format. And to do that, we're going to do this. Okay. We see that our log here has a base 4. So what that means is my exponential function will have the equivalent base. Okay. So here, um, the base of the log is 4. So that means that the base of my exponent is also 4. But because these are opposites of each other, let me introduce how we explained um, functions, right? As an input and output. So for instance, here in my log, my input is this value 16, and what the answer is, or our output, is x. So that's the opposite for my exponent. The output of the log becomes the input, the exponent of the exponent value of our base 4, and the input of the log becomes the output of the exponential value. So for the x is equal to 16, and see here we can see that what value has to be equal to x to get 16? Well, we know that if we have x is equal to 2, which is 4 squared, it's going to give us a value of 16. And we were able to solve it because here in this log format, I wouldn't know that. Well, I do, but I wouldn't be able to see that, oh, the log of 416 is 2, right? So we can do the same thing here. We can practice going vice versa. We can go from an exponent to a log if we needed to. So here we have an exponent of base 5 with an exponent 3, and our output is 125. Okay, so our equivalent or inverse log of this one would be a log. We write the word log, and our base is 5, just like my exponent. The input of the log was the output of the exponent, so that's 125, and the input of the exponent becomes now the output of the log. So that's 3. Okay. So let's do this one here with just the reference of the base b. So I want to convert this log into exponent. Again, the base is just b on this particular one. So I have b. The output of the log becomes the exponent of the exponent, which is 3, and the input of the log becomes the output of the exponent. So b cubed is equal to 27. Okay. How about this one? The square root of 81 is equal to 9. Well, one thing we can do is first convert the square root into its exponent value, which is 1/2. So we have 81 to the 1/2 is equal to 9. So now I can convert to the log. The base of this exponent is 81. The input of the exponent becomes the output of the log, which is 1/2, and the output of the exponent is the input of the log, so which is 9. Okay, so please keep in mind it's very crucial to be able to go from log to exponent and to exponent to log. Okay, all right. So these are some basic properties for our logarithmic function. Any log of any base, if my input is 1, my answer is 0. And what I like to do is I like to put in its counterpart, the 0 power for the exponents, right? So if I take any base exponent and take it to the 0 power, again, the answer will always be 1. Okay. What about our identity property? If I have a log of base a and I input that same value a, my answer is 1. Similarly, like my exponent, if I have a to the 1, the answer is just going to be a. But you see how we switched these? The input here was a, now it's the output. The output here was 1, now it's the input. Now these last two, I like to, or this third one is our inverse property, which is the ones that we're going to use a lot to, and again, for here, we see that we just switch them, right? We have log of base a to an exponent of x. The answer is just going to be x. The log and the exponents, you'll like to say that they cancels out, but it just gives us x. And similarly, a to the log of base a to the x. Again, the a will cancel with the base of the log a, giving me just x. And then the last one we've seen in exponents, but it's the same as logs, the one-to-one property. The one-to-one property says that for these two logs to be equal to each other, they have to have the same base and they have to have the same input value. Okay, so let's go ahead and look at some examples to solve. So we have the log of base 3 is equal to 1 over 27. So what I can do is I can convert that 27 to have a base 3. Okay, so I know that 3 cubed, and there's several ways, again, to solve, but one of the ways that I'm going to solve it is using the one-to-one property, which we practice right now. Let me see. Or never mind. Let me solve it instead, convert it to its exponential form. Okay, so let's do that. So if I'm going to convert it to its exponential form, I have this. The base of this log is 3, so that's the base of my exponent. The um, input of the log is the output of the exponent. So now I have this. 3 to the what power is going to give me 1 over 27. And this is where I was going to start with. So I can rewrite 1 over 27 as a base 3. So we have 3 to the negative 3. Again, I can 3 cubed is 27, but for it to have a base 3, I do the negative reciprocal, which gives me 3 to the negative 3. Now, if you see this, it's very easy to see what the question mark is. Should the question mark be? Well, the answer should be negative 3. Okay, so this is the answer for my log. Okay, all right. Now, um, if you see here, the properties that I used, I'm just going to go over them. This is the other, what I was just mentioning, that this is how I would have done it the first time around, okay, to solve. So let me go ahead and move forward to do another example. And again, I'm showing you that it's also represented as other examples is using our inverse properties. But I want to make sure that I do more examples. Let's look at this one. Use properties to solve. I have the log of base pi, which is just a symbol, and my input is pi to the 5th power. Okay, so if you see here, which property does this represent? It's my inverse property that says that when I have a log of base a and my input is that same base a, the answer is just going to be the exponent. So here, my log has a base pi. I'm putting in a value of pi to some exponent. So what is the answer? The answer would just be 5. Okay. All right. How about this one? This one should be super easy too. The log of base 7.5, and I'm going to input 1. What do I see here? Oh, that's my zero property for logs. That anytime that I put in 1 for the log, the answer will just be 0. So the answer here is 0. The log, the answer will just be 0. So the answer here is 0. Okay. All right. How about this one? Log of base 90 to 90. Here, what is the exponent here that the 90 has? We don't write it, but there's a 1. So our answer here is still, we're using the same property, our identity property. So the answer is just 1. Okay. All right, what about this one? Oh, this one is another inverse property, right? We have a base 3 to an exponent of a log of the same value, which is 3, and my input's 8. So what is the answer? Just my input, which is 8. Yes, and again, it's the inverse property. Okay. All right, so let's use definitions of logarithms to solve some of these examples. So for instance, here, I have a log of base b, and my value here is 1000. But how would I be able to solve or find what my base is if this is all they're giving me? Well, one of the things that I can do, if I know that that b to the 3rd power, so if I convert it to its exponential form, since I have a base b, my output is the input of the exponent, which is b cubed. This should be equal to 1000. So what base, when I cube it, gives me 1000? Well, hopefully we see that that's 10. 10 cubed will give me the 10,000. So what is my base? My base would be 10. Yes? All right, let's see. Can we do this one? Log of base 6 of x equals 5. So again, what I would do is I would convert it to its equivalent exponential form. As a log is a base 6, so that's the base of my exponent 6. The output is the exponent 5 is equal to x. So what is 6 to the 5th power? Well, that is 7,776. Yes? All right, let's see. I can do a few more. So let's look at some of our more properties, some more detailed properties for logs. And it's these 5 through 8. Okay, so this logs says that when I have a log of any base and I see that two things are being multiplied to this given log, I can expand these logs to two of them. This is the same thing as a log of base b of m plus the log of base b of n. And what I like to say, relate this one to is like the product rule for exponents. If I have 2 cubed times 2 to the 5th power, the answer is 2 to the 8th power, right? I just add the exponents. On this one, I'm going to add the logs. The quotient rule, if I have a log of base b, m dividing by another value n, I can expand this into two logs by having the log of base b of m minus the log of base b of n. Okay, and then this next one, 7, is called our power rule. That if I have a log and I have an exponent to it, I can multiply that exponent to a log. This becomes p times the log of base b of m. Okay, and again, this one is also our one-to-one property again. That if I have a log of base b of m equal to a log of base b of n, the only way that these two logs are equal to each other is if m and n are the same input values. Okay, so let me see. I have 3 minutes. I think I have time to just solve one really quick. Okay, so and this is a one-to-one property. You see that I have a log of base 5 on the left, a log of base 5 on the right. For these two to be equal to each other, the inputs have to be equal to each other. So again, this is my one-to-one property. So I'm going to set the inputs now equal to each other. X plus 1 should equal to 9. Solve for x, subtract 1 on both sides. So x is equal to 8. Again, I want to thank you all for joining us today. If you are here with me and would like to have a copy of our presentation, just click on that top symbol that has a box with an arrow pointing down. Thank you, Ms. Chuka. You can download it. Also, just keep in mind that these get uploaded to our EPCC YouTube channel. So again, have all good weekend and stay safe. I'll pass it on to our presenters.
Thank you, Mr. Carrizales. Thank you, Ms. Chuka. Yes, so Ms. Chuka had a little blue arrow on the screen. That's where you'll go and you'll click on it. So that way you could download the presentation. It'll download whatever's on the screen, okay? So again, as Mr. Carrizales said, we do want to remind you guys about the previously recorded sessions, which are available on a YouTube playlist. And this session will be available on that playlist later today. We did link a short survey to help us improve our TVE session. So if you guys could take a few minutes to fill out that survey, we would really, really appreciate it. And then now I'm going to share the TVE sessions that we will have next. So at 1 p.m. today in this same room, we will have a presentation by the EPCC Foundation with scholarship opportunities. We'll be back with Happy Math Hour on April 5th, so 2 weeks from now, at 11 a.m., where Math 1314 will cover properties of logarithms, exponential, and logarithmic equations, and Math 1324 will cover basic matrix operations and inverses. Our 1 p.m. session on April 5th will be a presentation on nursing programs and resources. Thank you all for coming in today. We hope you all have a lovely weekend. And if you have any questions, feel free to use the chat box or your mic. We hope to see everyone again for Happy Math Hour.